Okay, welcome back to the last lecture on witness sets. So I thought about describing the cascade algorithm, and I think as far as the background of everybody taking this course, it's probably best to skip this. You know there's a thing called a cascade algorithm. I'll describe it just vaguely today, and you can look it up. Okay. We already have a method for computing a numerical irreducible decomposition, albeit it might be really inefficient because we might have to track a lot of paths that end up landing on positive dimensional components or stuff like that. I don't think you're going to get too much insight into getting into the details of the cascade algorithm, which improves upon this. It's an important algorithm. It's state-of-the-art way of doing numerical irreducible decompositions. It's just I'd rather spend today talking about some other fun stuff you can do with witness sets instead of getting into the details. So it's the end of the semester. It's supposed to get more and more fun as we approach the end. So let's do that. So given our recent lectures, I asked you the question, what can witness sets do for you? So I claim they're the fundamental data type in numerical algebraic geometry, and we have gone over some algorithms of things you can do with them. So somebody give me one thing you can do. Okay. Find the dimension and the degree of some variety. Reducible. Okay. What else? Other than D. What else can a witness set do?
Oh, can reconstruct positive dimensional varieties.
What do you mean you can reconstruct them?
Or regenerate them from
Indeed, it represents positive dimensional varieties. Right, if you have a zero-dimensional variety, you just list all the points. Which, if you think about it, doing that is the same thing as computing a witness set for those points. Okay, so this really encapsulates a notion of solving. And it represents positive dimensional varieties. In what sense? Well, I guess that's the point of the question. In what sense is this representing my variety? What can I do with it?
you get like three things, right? You get the system, you get the complementary dimensional hyperplanes, hyperplanes, and then you get approximations for where those hyperplanes hit your varieties. So
yeah, that's what a witness set is. So what can you do with it?
Can you I don't know, I mean, you can reconstruct it. I don't know.
Sample generic points.
So those would be the random points, right?
Yeah, so some of these things are so staring at you in the face from the triple, which is a witness set, that maybe you don't even think that this is something you can do, or you don't even realize that this is a valuable thing for you. Okay. For example, dimension and degree, you just read off, right? You look at the dimension of the linear space, the dimension of your variety is the complementary dimension of that. That's all you do. Degree, oh yeah, it's the number of points in the witness set, right? So it's just staring at you in the face. Sampling generic points, yeah, just pick a point in the witness set collection of points. Okay. Yeah, and you can move the linear space around and sample more points. And what else can you do?
How can you move the, like, how do we move the hyperplanes in, say, Julia, for instance?
How do we move the hyperplanes?
Yeah. I mean,
Homotopy continuation.
do we get like the equations for hyperplanes inside the witness set that we compute in numerical irreducible decomposition?
Yeah, so a witness set in Julia in the homotopy continuation package is a collection of points, and it's also some linear subspace represented either intrinsically or extrinsically.
Okay.
And if you call witness set of a witness set in a new linear space, it'll move to the new linear space.
Okay.
So we'll do some of that later today. Did we not do that last? Maybe it didn't work last week. Okay. There are at least 2 more algorithms that we talked about that are on the code online. Yeah, okay, that's good. That wasn't even one of the ones I was thinking of. Decompose a reducible variety into its components. Okay, that's super important. If somebody just gives you a bunch of polynomials and they go, okay, well, what are the irreducible components corresponding to this? Like do a primary decomposition. That is a hard symbolic task. Numerical algebraic geometry thinks about it as a geometric problem, where it's not actually so difficult to do. Okay. So we're really bypassing some of the difficulties of these algebraic geometry tasks. But we do so at a cost, and that cost is that all of these theorems that we're using, which legitimize these algorithms, rely on generic choices of some objects, which you can never be 100% sure you have. Right? So a witness set requires a generic linear space of complementary dimension. And indeed, you know that you must be the unluckiest person in the world to randomly pick one that doesn't work because it happens with probability 0. But that's not a proof. That's the kind of evidence you bet your life savings on, but it's not a proof. So the next section is what can you prove about numerical computations. Okay. So that's the cost of bypassing these otherwise very difficult algebra geometric tasks. What else can we do? What if we have 2 varieties and we have witness sets for both of them? What might we ask? One's a subset. Variety containment. If you take a course in symbolic computational algebraic geometry, you're probably going to be thinking about Grosvenor bases. The motivation that lots of texts and discussions have about Grosvenor bases is that you want to solve the problem of ideal membership. So you have some collection of polynomials. They generate an ideal, all polynomial combinations of them. And then somebody hands you a new polynomial and says, does that belong to the ideal? So that's an algebraic question. The geometric point of view of it is basically you have a bunch of polynomials, you have some variety, somebody hands you a hypersurface and asks, is your variety contained in that hypersurface? Okay, up to scheme multiplicity stuff, that's what that question is geometric. And so I'm saying the fundamental motivation behind Grosvenor bases is pretty immediate with witness sets. I can check very fast whether or not my variety is contained in a given hypersurface with probability.
Is there any relation between witness sets and Grosvenor bases? Like, is it like, are they geometric and algebraic analogs of each other?
Yeah, so this is a good question. So the question is, what is the relationship between a witness set and a Grosvenor basis? And the answer is that they are exactly the same in the sense that they represent varieties to a computational algebraic geometry. And I think that's pretty much where the buck stops. You can ask about the geometry of a Grosvenor basis. Sure, and if you have, so if you have a Grosvenor basis, you do it with a particular monomial order. And so whatever the geometric interpretation has to respect that monomial order. So if you do a lexicographic order, talking about projections onto coordinate linear spaces, and you can think about things that way. But otherwise, yeah, I don't. Grosvenor bases are really algebraic gadgets, where the geometry is obfuscated.
Yeah, but like, yeah, okay. I was just asking because like there is a variety and ideals are like equivalents of those things, and I was thinking there might be more connections because they seem so it seems too similar to be.
Yeah, so indeed, when you compute a witness set, you're finding the zeros of a zero-dimensional variety, so a zero-dimensional ideal, which is your equations plus a bunch of linear forms. But a Grosvenor basis for a zero-dimensional ideal is a little more. Okay, great. And so from variety containment, we get variety equality. The holidays are coming up and we might be constructing our wish lists for gifts. Is there anything you'd like to add to the wish list of things that you want to know about a variety? You have a variety that you care about. You almost certainly do, if you think hard about it. What do you want to know about it?
Smooth.
Is it smooth? That's a good question. So can a witness set check if X is smooth? Good. Anything else?
Homology.
Logical. Homology? What else? Be creative here.
The genus.
Genus, sure. Anything else? Okay, so if you liked this course, any question like this is a great thing to investigate. Okay, from a numerical algebraic geometry point of view, can I get my hands on any of this? Smooth, yeah, you write down equations for the singular locus, you do a numerically reducible decomposition, see if anything pops up. And then you could just write down a singular one of your variety. Okay. Topological info, we'll talk a little bit about this today. Genus, well, there are genus degree formulas which have three ingredients. You have the genus, you have the degree, and you have some measurement of all your singularities, for example, for plane curves. So if you know how to extract information about the singular locus and the multiplicity of those singularities, and you know the degree you get from a witness set, you can compute the genuses. Okay, what else? Anything else?
Where do you say you can compute the
So there's a formula relating for plane curves, degree, genus, and a singular point sum. So basically, there's a relationship between genus and degree, which fails to be an equality measured by how singular it is.
Yeah, is it
One of these, I don't want to say out loud.
I thought
I call it the degree genus formula. And so if you were able to extract information about the singularities, you would have the degree and the information about the singularities, and that's 2 out of 3 parts of the equation you could write down with the genuses that way. Recursive. Okay, great. Yeah, so anything on your wish list, either try to look it up or write a paper called Computing Blah with Numerical Algebraic Geometry. Great, good. Okay, so what are we going to talk about today So interestingly, so I really appreciate none of you wrote down one particular answer, though it is an answer that we're going to talk about today, is the equations for the variety. Right? So that wasn't on the wish list, which means I did a good job of taking you coming in here, being very focused on equations for varieties and saying, don't worry about it, because you're not even mentioning it at this point, but maybe you want equations. Because remember, you don't need to have equations for your variety to have a witness set. Because it might be the image of some map where you don't have the equations. Right? What you have is equations for the graph upstairs. You have like this witness pseudo witness set, but you don't have equations for the actual thing. Maybe you know. Real topology, like I have a plane curve. How many components does it have? How many connected components over the reals? Yeah, for example. Okay. So that's what we'll check on. Equations and real information. Which one do we want to do first? Any opinions?
The equations.
Awesome. How many conics go for 5 points? Anybody know? Seeing nods, but we're not hearing numbers.
One.
One? Yeah. One, generic. Okay. Why is that the case? Well, what does a conic look like? When I say conic, I mean like a plane curved degree. It has to look something like this. So somebody writes down 5 points for me. P1, P5. Call it X1, Y1, X5, Y5. And I task you with the problem of finding the conic through these 5 points. So I gave a talk about conics in math, and I asked like high school, grade school students to find the conic through 5 points. So as us mathematicians, how do we do it? Well, how about describing all the conics just through P1? Well, that would mean a Q of P1 was 0. Okay, but that's a linear equation. Because remember, these xi's, yi's are all numbers. So that's a linear equation in the A's. So let's call that L1 of the A's. So L5 of the A's. And we write these linear equations in a matrix, and we solve it using linear algebra. So what does the matrix look like? Well, remember, we're trying to find the A's, and we have linear equations whose coefficients are given by the monomials in the xi, y's. So this is 1, x1, y1, x1 squared, x1, y1, y1 squared. Remember, this is a row of numbers. Somebody's given us x1 and y1, and I want A naught naught, all the way up to A02 to be the zero vector. Okay, so I got 5 equations, 6 variables. If they're generic, I expect this to be a full rank 5 by 6 matrix. And so its null space has dimension 1. Okay. So there are infinitely many solutions to this linear system, but all of them correspond to one conic. Because any point in the null space of this matrix will give me some equation for the conic, and any scaling of that point, i.e. anything in the vector space spanned by that one element I chose in the null space, defines the same conic, because if I scale a polynomial, I have not changed its zero set. Right? Make sense? So what if I had a conic? But I didn't have its equations because it's like a projection of some curve in some high dimensional space. Okay. And I wanted to find the equations for it. This left board here tells me all I need to do is to be able to sample a bunch of generic points on it. 5. We know how to sample generic points using witness sets. So we'd use our algorithm to sample 5 generic points. We'd write down the system of equations and we'd solve them. This is called interpolation. Okay. And people study how to do this very well in numerical linear algebra. Okay. Okay, maybe you sample 50. Okay. Sample 50. And you have a 50 by 6 matrix. How many elements do you expect to have in the null space of a 50 by 6 matrix? You expect 0, except these aren't just any old 50 rows. You know there's a solution because there's a conic through them. Right? So this is still, if you sample a bunch of points, it's still a rank 5 matrix. It still has a conic through it. Right? And so if you want, sample a bunch. Now you have an overdetermined system that you know has solutions, right? So you're solving via least squares, or via you find the null space via like a singular value decomposition or something like this. Okay. Point is, if you know there's a solution and you're able to get a bunch of data, great. Numerical linear algebra has you covered. You can compute a numerical null space of a matrix. You just call null space in Julia, and it'll give you something. Okay. Questions? This matrix is called a Vandermonde matrix. Okay, when people talk about the Vandermonde matrix, they mean the one where the monomials are 1, x, x squared, x cubed, all the way to x to something. Okay, but that's just a very special case of choosing your favorite monomials and then evaluating at a bunch of points those monomials.
Wasn't there some theorem that determinant of that guy was resultant of that polynomial or something?
For the univariate setting. Okay. Awesome. So that's for conics, very simple situation. Okay, but what if I have a more complicated situation? So first of all, what ingredients did I need to be able to do this process?
You need to find the degree, and then you wanted to find the sample, be able to sample points.
First thing I need to do, well, there's 2 things, that's exactly right. So the first thing is I had to be able to write down at least an over approximation of which monomials might appear. Okay, so I needed to know this 3. If I thought that my variety was degree 1, then I would have just had something by 3 matrix. And I might try to find the null space and there wouldn't be any. And that would tell me there's no line through my 6 or 50 points. Okay, so I need to have guessed the monomials well enough. And indeed, if I know the degree of my variety, then I have an over approximation of the monomials. Because I know the degree, I know the number of variables, and I know there are only finitely many monomials up to a particular degree in a particular number of variables. Specifically, E plus n chooses D. Okay. Okay. You do a -1 if you want it to be exact.
Oh, okay.
Okay. So this is less than D. Awesome. Great. So like, let's think about how that works. All right, so let's say I have a map B. Goes from CT squared. And it goes over to C cubed. X, Y, and Z. 2 parameters of here, going into a 3-dimensional space, I'm expecting a surface. If I'm expecting a surface in a 3-dimensional space, that's a hypersurface. And if I have a hypersurface, it's defined by 1 equation. And we want to find that equation. Okay, and say ST goes to great. I map ST to a triple of degree 7 polynomials. Step 1, I need to know a bound on the degree. What is the degree of the image of this map? Got flat space here in SNT. It's mapping over to some curvy surface in 3-dimensional space. What is the degree of this? Well, no numerical algebraic geometry required for this one. It's the intersection points of the image of this map with 2 hyperplanes. Right? So if this is X, Y, and Z, I'm taking 2 linear forms of these expressions. That will give me 2 equations in 2 variables. Each of those equations has degree at most the maximum of these degrees, because I'm like doing like 5 times this plus 3 times this plus 2 times this plus 20. That's a linear form. Okay, so I'm really just trying to compute the zeros of 2 degree 7 polynomials in 7 variables. Right? And that tells me that this has degree less than or equal to 49. This is Brysiewicz theorem. Okay, cool. So whatever this matrix is, the number of columns will be 49 plus 3 choose 3. It's approximately 20,000, I think. Okay, big. Yeah, 22,100. In particular, I'm going to need to sample at least 22,100 points. Okay. How do I sample 22,100 points? Again, no numerical algebraic geometry required. I just pick a bunch of random ST values. Maybe like 30,000 of them. Get a bunch of values.
Choose 3 should be choose 49.
Oh, that's the same thing.
Yeah. Oh, yeah, right.
Yeah.
You don't have to worry what goes on the bottom. N or D. Okay, great. So now all I gotta do is find the null space of like tens of thousands by tens of thousands. That's within the realm of numerical linear algebra, but you might be pushing it a little bit. Okay. And also you want to make sure that the points you're sampling are sampled with really, really high precision. Because the conditioning of this problem might be very bad. And if you don't know what any of those words mean, take a numerical analysis course. Okay. There's a measure of the numerical difficulty of solving a linear system of equations measured by a so-called condition. Okay. Okay. Any questions?
So the 49 is a Bezier bound, right?
Yeah.
So that I am clear about. How did you get that? Could you walk me through the process of finding the degree again? Sorry, I know it's a bit.
How to get 49?
No, the degree that the one which you mentioned that you take two linear forms, you intersect it, and that.
Yeah, that's how I got 49.
But isn't that the Bezier bound?
So Bezier tells you how a bound on the number of solutions to a square system of a particular degree sequence. It does not tell you, at least immediately, a bound on the degree of the image of a map.
Okay.
Right? So let's give these names phi1, phi2, and phi3.
All right.
So my first equation is like 3 plus x plus 7y plus 12z. That's a generic linear form. And my second one is 7 plus x, 3x plus 10y minus 11z. Okay. And I want to solve this. I can solve it by pulling it back along this parameterization. So I'm replacing x, phi1, y with phi2, z with phi3. So this is this parameterization lesson we had. Like that. Okay. So now you expand this. What is phi1? It's a degree 7 polynomial in two variables. What is phi2? A degree 7 polynomial in two variables. What is phi3? A degree 7 polynomial in three variables. So the sum of them is a polynomial in two variables, s and t. So the sum of them is a polynomial in two variables of degree at most 7. Same here.
Yes.
And so I am trying to compute the zeros of two polynomials, two variables, degree at most 7.
Mm.
That from Bezier scored.
Okay.
Now the thing is, that's a bound, but lots of times it's smaller. Right? For example, this image has degree 7. Okay. 7 plus 3 is 3.
Benches.
All right, so you can use the Bezier bound and solve like a tens of thousands by tens of thousands matrix. But you may be like drastically over guessing the degree. So it's really good to know the degree of the thing that you're trying to interpolate, because you will significantly reduce the linear algebra problem you have at the end of the day. Oh, well, how do you find the degree of the image of a map? Good thing we have witnesses. Yes. And sampling, of course, can be done via witness sets. And one can ask whether or not that's better or worse than doing random sampling of the parameter space. And that will just kind of depend on what distribution you put here and what distribution that induces over here, and whether or not that makes for a nice linear algebra problem. But that's not the only reason numerical algebraic geometry is good for sampling. It's also good for sampling because you might have varieties you're interested in, which are images of maps, not of some c to the k, but of some other variety. And then really, how do you sample from that? you can't just pick a random thing because you have to pick something random on the variety first, right? So for example, let's say, so here's a good question. And you can imagine somebody never thinking about algebraic geometry and liking this question. Are there any conditions on the 2x2 submatrix of a 3x3 orthogonal one? So here's what a generic 3x3 matrix looks like. Asking that's orthogonal is this matrix times the transpose equals the identity. Those are polynomial equations. Turns out that the zero set of those polynomial equations gives you the algebraic closure of the orthogonal group O3. Okay, that's a three-dimensional thing. So ON has dimension n choose 2. So we got a three-dimensional thing. My question is, if I just project onto like these coordinates, is there any equation that has to relate these coordinates? In other words, if somebody gives me just 4 random numbers here, complex numbers, can I always complete it so that that matrix times the transpose again? Okay. Well, I have a 3-dimensional space, and I'm projecting onto a 4-dimensional space. So there's got to be at least one equation between these, but it's not clear what it might be. You know the equations for the orthogonal group is that like each row, each column have to have unit norm, and any 2 rows, any 2 columns have a dot product at 0. But none of those only involve these 4. Okay, so how would you approach this using numerical algebraic geometry? First, so let's do it. Find a witness set for this 3-dimensional space, 3-dimensional variety in 9-dimensional space. Okay. Use that, sample a bunch of points. Okay. Project onto the first 2x2 submatrix. Now you're sampling a bunch of 2x2 submatrices of 3x3 orthogonal matrices. Okay. Do interpolation. So that's how you would sample from this space of 2x2 submatrices of 3x3 orthogonal matrices. You would just pick a bunch of 3x3 orthogonal matrices and just look at the 2x2 submatrices.
Okay, so if I understand it correctly, pick generic points up there in 3, project them down, and then complete those points.
So after you project them down, now you have a sample of the variety you're actually interested in,
Right.
which you know is a subvariety of a 4-dimensional space.
Yes.
You'd like to know a bound on its degree. Okay, that's bounded by the degree of the orthogonal group. Okay, so you have a bound on its degree, you can sample points, you can do interpolation. Okay. If you're a symbolic algebraic geometry, you'd be doing elimination for this process.
Is there a benefit to one done?
Yeah, so the question is there a benefit of doing this interpolation versus doing elimination? Okay. Yeah, in almost all moderate to large cases, you can't do elimination. In particular, like, how does it work? Well, you say eliminate to your Macaulay 2, and you wait, and you pray that that's what you do. And maybe you get an answer, or maybe you don't. And if you're more advanced, you can kind of get some like intermediary output, kind of telling you whether or not you should expect an answer. But in general, it's kind of an all or nothing story. Now, the benefit is that if you can compute it, it's a proof. On the other hand, if you do things numerically this way, there's really no particular part of this that's like the big impossible bottleneck, except maybe solving the linear system of equations. Okay. Like sampling, like getting the witness set is fine. Like you don't even need a full witness set. You can just do monodromy and get some points. Right? You don't even need the full witness set. As long as you know like a bound on the degree. Okay. You're just trying to sample points. So that's going to be super duper fast. Cooking up the matrix you want to solve will be super duper fast. Solving it may or may not be, depending if you're a matrix in the hundreds of thousands or not. Okay. Yeah. And at the end of the day, what you're going to get is a description of the null space of that matrix numerically. Okay, so you're going to get one or many vectors in the null space, which represent floating point approximations of your coefficients. Which means you're not going to have an exact equation. You have a pretty good one. And then there's a whole industry of trying to get the exact number from the floating point number. And if you want, we can talk more about that later.
The elimination gives you exact numbers, whereas
Elimination gives you exact numbers with exact input. Right? Because almost always with these problems, your input is over the integers of the rationals. Right? The equations for a matrix times its transpose equaling the identity, like that's exact. It's ones and negative ones everywhere. Right? Any other questions? Okay. I really do want to talk about the understanding the topology of the real locus of curves. But I see that it is 11:20. So I'm gonna stop. We're gonna take 10 minutes. You come back. I'm gonna talk about that, and then we'll do some computation. Maybe we'll try some interpolation or something like that. Okay. Sound good? Awesome. All right. See y'all in a bit. Okay, welcome back, everybody. So we're going to continue the lecture and maybe hop on a computer somewhere in the middle. We'll see how the timing works. So on the board here, I've drawn some plane curve. And you'll notice that since I've drawn a real picture, the curve is not connected. So for the complex numbers, the curve's connected. This is what allows us to move from any point to any other point when doing witness set computations, for example. How many connected components do you see on the board? 4. I want you to think for a little bit how you might compute that number 4 using witness sets. Can you? Actually, give me any way to compute the number 4 other than plotting it and looking, which is not a reliable way.
Just compute the homology zeroth group, but
How? All you have is the equation. Oh, that's interesting. So tell me more.
You have a monodromy group, so then you look at the, I guess, what like how the permutations that are possible.
Okay. So if you're talking about the monodromy group of the witness cover, we know that's the full symmetric group. Because we know that we can restrict to just a parallel family of lines. And then the points at which we meet the exceptional locus are the tangents lines in that family to the curve. And generically, we're only tangent at a single point, and so we're generated by transpositions. Only transitive group generated by transpositions is the full symmetric group. And so the monodromy group is going to be pretty boring. It's just going to tell us the degree. Now, there's a question of like, well, look, there are like ovals here, right? So maybe there's like some sort of notion of like a real monodromy, perhaps, and like people think about this. Margaret Reagan is a good person to check out her talks about this. So exactly what can be well defined over the real locus and in terms of monodromy, and how does that play with numerical algebraic geometry, and how can that make algorithms more efficient? But I'm not seeing it exactly. I mean, I guess spinning around a family of lines where like they all intersect at some point inside the oval seems like a plausible move, but pretty soon you realize that some adversaries might come at you and draw an oval like this. And that's going to look like a less promising method, because as you swing around anything, you're going to be tangent and lose real points.
Why did you say the monodromy group was
The full symmetric group on the degree of the curve.
oh, if it is disconnected, what is that?
Connected over the complex numbers. So if you want to think about things over the reals, your task is actually to define a monodromy. Right? So like, for example, like take a slice. Now imagine moving that slice around and eventually coming back. I guarantee you that as that movie plays in your head, you change the number of real solutions at some point. And that means your points have come together, which means you went through the exceptional locus, which is a no-no in monodromy. So you can, so again, you can ask yourself, well, what can I recover? Like, can I get like some partial information? Maybe, but that's an open area of research. Okay, so let me tell you. Which meeting? So first of all, let's do a generic projection onto a line. Okay. Now, one way I can do that is pick some direction and project everything to a line orthogonal to that direction. Or dually, I can just randomly move the curve with a rotation and then just project straight down. Okay, and since I like my projections to go downward on the blackboard, we're going to pretend that happened. Okay, so projecting straight down to okay, so downstairs there's an exceptional locus to this D to 1 branch cover. And in fact, you can think about fibers as computing witness sets in a parallel family.
Is it generically equivalent if you're considering only the real part?
Say again?
Is it generically D2 if you're considering only the real component and not the complex one?
No. So indeed, so there's a positive set of positive measure where I get different numbers of real solutions. So when I say this is a D to 1 branch cover, I mean over the complex.
Okay.
Yeah. And since this projection was generic, that's the same thing as choosing a generic parallel family of lines. So you will really get degree of the curve many points over the complex numbers. Okay, but so we have a branch cover of a line. It has a finite set of exceptional points. Homework. What do they look like? Well, one there, right? There. That's supposed to be there. Am I missing any? Oh, that looks good. Right. So it's all the places on the curve with a vertical tangent line or all the singular points. So if there was a singularity, like 2 count dots, like that would also count as a point in the exceptional locus. So downstairs, these finally many points are called the exceptional locus. Upstairs, it's the ramification locus. Okay. All right, so good. Okay, so now name of the game. Compute fibers in the middle of all. So up here. I have 2 real points in a fiber. And only when I pass one of these exceptional points can that number change. Here. I'll have 4 real points. Makes sense? Okay, and also notice that in between these exceptional points, there's nothing topologically interesting happening upstairs. There are 4 real points, these basically just like look like 4 of the last. Maybe at the very end point something interesting is happening, but in the interior, no. Just a 4-sheeted covering space over the roofs. Okay. Pictures always end up looking a little complicated, but on computers. So far, so yeah. Okay, notice that over each exceptional point, in this case, we only have 2 points coming together. And that's a property of being this generic projection. Okay, now if there's like a singular point with multiplicity, maybe something else happens. But for now, I just want to convince you that using homotopy continuation, like for example, as you move from like this ribbon to this ribbon, you know which of these points are colliding. Right? So you can do this in a few ways. One, you just get really close to the endpoint and see which 2 points are coming together. Another way is you can just do a little monodromy loop and see which 2 points are permuting. Right? So you can do all of these things. Great, and that tells you at the endpoints which points come together. And so that gives you a way to draw things like this. Okay. So again, so I start here, and then I move from here to here. Okay. Now these points are smooth, so the homotopy paths follow just fine. Here. Right, so I can really do homotopy continuation from here to here, and it's all nice and dandy, which means these 2 are not involved in any interesting coming together. Okay. And so when that happens, I just draw a line segment between those 2 nodes. Okay. Now these 2, they came together, so they get to have a new like birthing point right here to indicate that they've come together. Okay, and then I repeat that again. So I take these 4 points, I move them over, all of them are moving over quite smoothly, and so I can just draw. Over here, of course, 2 of the complex numbers come together. So I get a new birthing point. I know exactly which 2 because it's the 2 new ones. Okay, I do it again, and this time I actually see 2 dying. So this is their birthing point, this is their death point. The other ones follow smooth. And at this point, you see what's happening. I'm building up a graph, which is going to have the same topology as my curve. Okay. Point. Point. What you see here is like this polygonal approximation of the curve, which reflects the topology. And do you know how to take topological invariance of graphs? Yes, because they're CW complexes, right? It's algebraic topology 101. And if you don't know how to do that yourself, there are software packages that do. Just plug in a graph and say, yeah, tell me how many holes, tell me how many connected components, and it'll tell you. Okay, but like with so many numerical algorithms, this relies on some genericity of my projection and some reliability of my homotopy continuation. So this is all subject to the promise that homotopic continuation was implemented. And your tolerances are sufficiently tight. All of that. That makes sense?
It's a cool idea.
Super cool idea. Yeah. And this is beefed up to three-dimensional varieties, varieties in three-dimensional space, surfaces, and implemented in a software package called Bertini Real. So before Julia's homotopic continuation package existed, there was Bertini. Bertini still exists. Still totally awesome. It's very, very reliable. And there are packages in Macaulay 2, which make it really easy to use. Okay, so I encourage use of Bertini. But I had to pick something for the sake of the course. So I picked the Julia one. And then Bertini Real does this real decomposition and can do so for surfaces as well. And from that information and samples, you can create 3D models of varieties like this one. Pretel, would you hold that up to the camera? So this is the Barth sack stick. And this was created by Sylviana Amethyst. So she does some 3D printing. She's also the main developer of Bertini Real, as far as I know. So yeah, this is great. So this is a sack stick surface. And yeah, so an interesting thing is how do you deal with singularities? Singularities we know play kind of poorly with numerical algebraic geometry. And it also plays pretty poorly with 3D printing, okay? Because singularities are infinitely itty-bitty, which makes them infinitely fragile. So how do you deal with that? Well, there's this great idea to have these little plugs to connect the singularities together. So this is a great surface, super symmetric. It holds records for some sort of geometric properties, maybe the number of nodes or something. So you can pass it around, you won't break it. Yeah, so this kind of idea is souped up in Bertini Real, and you can do 3D models of varieties and stuff. Okay, so that's fun. So that's another thing you can do with numerical algebraic geometry / witness sets. You can interpret this process as just moving a particular family of witness sets around.
So does the numerical irreducible decomposition, does it do something like this or?
No.
That's
No, over the complex numbers, the numerical irreducible decomposition finds witness sets for every pure dimensional component and then does monodromy breakup on each of them to bust it up into the irreducible components in each dimension. And it does a little bit more depending on the multiplicity of the components, but we didn't really cover components with multiplicity. Okay, great. So that's it for witness sets. And next class we'll talk about certification. So actually getting proofs out of things. So along with the question, well, that I hopefully inspired you with, like, what can you possibly want to know about your variety and can you compute it in numerical algebraic geometry? You can ask exactly those same questions in terms of certification. You can say, okay, we've learned how to do a bunch of stuff in numerical algebraic geometry. Can we certify any of it? Okay, so I am going to give you an answer that says, yeah, you can certify at least some of it next week. And it will be up to you and the community of numerical algebraic geometers to try to extend those certification methods to the algorithms we talked about. Okay, I'm going to pause. I'm going to take a little bit of questions and then we might jump back into a computer session or maybe not, depending on how many questions. Okay.